Welcome to my channel again. Let's discuss how ChatGPT works. So basically, let's say we gave ChatGPT some prompt such as what is the capital of India. For this prompt, it might answer something like the capital of India is Delhi, or Delhi is the capital of India. Now you might be thinking, how did it construct this sentence? Or this sentence, for instance. So basically, how any large language model such as ChatGPT or Gemini works is basically there's something known as context. Yesterday it rained. If I say the sentence to you, you might think that where it rained or why am I telling this to you at all? So you need a context, right? So in the very same way, every large language model needs a context and it maintains that context. So for example, when the user inputs a prompt to the LLM, this entire prompt is treated as context. So this is the context right now. I'll term this context. This is the context. Now this context is fed into the LLM. And then a list of words are given some probability. So basically, let's say there's there's Anne, there's Delhi, or Ladakh. Just an example. So these words, there will be bunch of random words, and all of the words will be given some probability. So let's say A has been given a probability of, let's say, 1%. Just an example. And Anne has been given a probability of 7.8%. And then the has been given a higher probability, let's say 60%. Delhi has been given some probability, let's say 20%. And Ladakh has been given a probability of 0.5%. Now we must know that there must be other words too. I'm just giving 5 examples, but there are a lot of words and each of them are assigned some probability. So amongst this probability, the model chooses the word which has the highest or second highest or third highest probability. And this process is randomized. So let's just say it always chooses the highest probability word. So for now, it will choose the. Now, the will be added to the context. The will be now a part of the context. Now this entire context will be again fed to the model. Now the probability will be regenerated and we'll again get some words. I'm just typing random letters, but these are some words, and there will be Delhi 2 and Delhi and capital. All of these words will have some probability again, let's say 2% and some percent again, like some percent. And Delhi will again have some higher probability, 30%, let's say 30%, and capital will have again some higher probability, 40%. So the model will choose the word with the highest probability. This is not how it works, but for now I'm just saying that the model will choose the word with highest probability. Let's say it chooses capital. So the next word, capital, will be added to the context. Now this entire context will be fed back to the model again. And then again, some list of words will be generated and the next word will be chosen. And then again, the list of words will be generated. And then the chosen word will be added to the context. And then the context will be again fed to the model. So this process keeps on repeating until the model thinks that the sentence is complete or the answer is complete. So, but this is not exactly how it works. How it works is it also randomizes its choices. For example, it never chooses, like it is not like it always chooses the word with the highest probability. It also randomizes its choices, such as it might choose the second highest probability or third highest probability word. And that is exactly why when you enter the same prompt twice or in different devices, you expect to see different answers. And that is because it has randomized its choices, and it's not that it chooses the highest probability word all the time. So for example, these two are the possible generations that it can do, and that is exactly because it randomizes its choices. If the process was not randomized, then this would have been the answer all the time, like legit all the time. And if two people had put in the same prompt, then they would get the same answer all the time. But this does not happen, right? We always see different answers for the same prompt, and that happens because of the randomization process. So today, let's actually build a ChatGPT, but in a very small version, like a very mini ChatGPT thing. So what I have done here is I have imported some libraries and I have imported this data set, names. Now names has len of names. Names has 32,000 names. And let's give some examples. Let's see what these names look like. The top 10 names are Emma, Olivia, Ava, Isabel, Sophia, Charlotte, whatever. So these are the names that are present in the names dataset. Now what today we are going to build is something very similar to what I explained you just now. We are going to build a name generator. And what that will do is, instead of taking one word or the entire list of words as context, it will take just one letter as a context and it will try to generate the next letter. For example, when we enter E, we expect to get M. And when we enter M, we expect to get M again. But this process is a bit difficult, considering that we are taking only one letter as context, because for the same letter, we might get different next letters. For example, for A, we expect to see V, but then for A, we also expect to see M. So for the same letter, we can have different outputs. So the model won't be 100% accurate, but at least we'll be able to replicate some portion of the LLM. So what we'll do here is we'll make a chars variable, or let's say join names, and this entire thing will be a set, will be a list of chars. Now if we print chars, we'll just get ABCD, basically A to Z, but we want this to be sorted, so A is sorted. Yeah. Now we'll print this. Yeah. So we are getting A to Z in a sorted manner. Now what we'll do here is we'll try to kind of get the bigrams. This is a bigram language model. So what we'll do here is, for name, or let's say word in names, we'll just take 3 names for now. Name equals to, what we'll do is we'll concatenate the names with full stop before the name and after the name. What will be the, why am I doing this? I'll show it to you right now. For let's say I comma j in zip of name comma name of 1, print I comma j, and then we'll print. Yeah, this should be good. Yeah. So why I added a full stop before and after the name was to represent where the name is starting and where the name is ending. So when we enter a dot, we expect to see E, because E can be a starting letter. And then when we input E into the model, we can expect to see M. Then for M, we expect M, M for A for dot. Then again, for the next name, for when we input dot, we expect to see O. For O, we expect to see L, L for I for V, V for I. So you get my point. So now let's actually create a map. First of all, let's create a story, which will be S comma I plus 1 for I comma S in what will be, okay, yeah, tab. So if we print S to I, this will basically map every single letter to a number. So A has been mapped to 1, B has been mapped to 2, and dot has been mapped to 0. And for ITOS, it's the other way around. ITOS will be 1 has been mapped to A, 2 has been mapped to B, 3 has been mapped to C. This map will help us do a lot of things. So let's now create a dictionary. Let's say bigrams equals to a dictionary. And what this dictionary will do is, for word and names, we'll create name again, and we'll do the same process. But this time, instead of printing, what we'll do is a list of word plus, yeah, for I comma j in name, sorry, zip of name comma name of 1, what we'll do is, yeah, so here we see what we have got here. If we print bigrams, what I've done here is made a dictionary, and instead of printing I and j, I have concatenated them, basically made them in a tuple, and for each tuple I have incremented a value, incremented it by 1 for in the dictionary. So basically dot e has occurred 1500 times, and then em has occurred 769 times, and has occurred 168 times. So you basically get my point. So this is basically a dictionary mapping each tuple to values. But let's do it in a better way. Let's actually clear output. Yeah, let's do it in a better way. Let's make n, which will be a torch dot zeros of 2, 2. Yeah, let's print n. So n is basically a matrix of dimensions 2, 2, and each value has been zeroed out. Now instead of 0, if I do ones, we'll get 1, 1. Okay, so let's start by 1. We should have started by 0, but I'll start by 1, and I'll explain why I have started by 1 later. But let's start by 1, and instead of 22, we'll do 27, not 26, because we also have a dot. So this will be a vector of a matrix of 27 by 27. We'll clear the output again. Yeah. Now let's perform the same task again, but this time in a much better way. Let's do this for a word in names. Name, yeah. Name equals to, yeah. So now if we print n, we'll expect a much better result. Instead of printing it the way we got before, we'll get this. Okay, so let's do something. This will be d type equals to torch dot int 32. Don't print. Oh shit. Clear output. Yeah. And this will be much better. But yeah, but we also want a way to visualize it, right? So I'll just do this, and I'll run that, and now we'll be able to visualize everything in a much better way. Yeah, so here we see that dot dot occurs 0 times because no names are of length 0. So dot dot represents that the name starts and ends with a dot dot. So that means the length is 0. That means no such name exists. That is why we are getting 1. And remember, 1 means 0 because we have initialized the matrix with 1 itself. Now dot A occurs 4,411 times. Dot B occurs 1,307 times. Dot C occurs 1,543 times. So you get my point. This is basically a mapping of every consecutive letters, and we are getting how many times each of these occur. So for example, RI occurs 3,034 times, ON occurs 2,412 times, N, names ending with N occurs 6,764 times. So that's a lot. So basically, this is a character-wise mapping. Now what we'll do is, we'll print n of 0. This will just give us the first row, right? This will give us the first row. You can see this is exactly the first row, 4,411, 1,307. This is the first row. What we'll do is p equals to n of 0 dot float, and then we'll divide p by its sum, p dot sum. Yeah, and then we'll print p. Okay, sorry, yeah, p dot sum. Yeah, so right now what you see is there are 27 values. These are n itself, the first row of n itself, but then each of them have been divided by the sum of the row. So what we are seeing is basically the probability. So what I'll do is I'll try to make it simpler. I'll print p dot sum first. P dot sum is 32,000 something, 32,060. What I'm doing is I am literally dividing every value of n of 0, which I printed before. I'm dividing every value of the first row by that 32,000 number. So p divided by its sum, and p will be this. This is basically probability of each letter, each bigram occurring. So if you notice, the first bigram has a very low probability, e to the power minus 5. So that is a very low probability. But then this first bigram has a very high probability, and that is because a names starting with A have a probability of 4411. That is why it has a very high probability. So this is P. Now what I'll do is, instead of just dividing the first row, I'll divide the entire n matrix by its sum, by the sum of each respective row, comma, keep dim equals to true. Yeah. So if I print the first row again, we should get the same answer. Let's print first two rows. So this is what we get. So what we are trying to do here is, now we'll try to get, now technically what should, if we were to generate a normal name generator, what we should have done is, we should have taken the first letter, like the most occurring bigram in the first row. So the most occurring bigram of the first row is dot A. Name starting with A is 4411. We would have selected that. So the name would have started with A, dot A, and we would have gone in A's row. In A's row, what is the highest probability or maybe occurring bigram? And that is A itself. So for our model, normal programming name generator model, this would have been the end, because we are constantly selecting the letters or bigrams of the highest frequency. For example, what I just gave you right now. But let's just ignore this. We would have gotten AN because it has the highest probability, 5439. So we would have gotten this name, N, AN, and then we would have gone in N's row. And then again, you see, N is the ending bigram of most of the names. So we would have again ended with AN. Now this, you see, the problem is of a normal programming name generator, because what we are doing is we are constantly just selecting the bigrams which have the highest frequency. So we would have either ended with A or with AN, but that doesn't make sense, right? Because this map has been created from legal names, right? From these names, the entire data set. So this does not make sense, and we want a more natural name generator. And let's just again ignore N. Let's go to some other frequency bigram. And A is again a higher frequency bigram. So A and A. And then we would have gotten again the highest frequency, A. So Anna. Now this name still does make sense, but you get my point, right? We had to make 3 exceptions just to generate one name. And this wouldn't have been possible with a normal program, with if-else statements, with a for loop, if we had to choose the highest occurring frequency bigram every time. So what we want is, we want a probability and a generator that will generate names for us and in a randomized manner. Just like what I explained you in the starting of the video, ChatGPT does not choose the highest occurring frequency all the time. That is exactly what we want to. We want randomized choices. We'll copy paste this code. Yeah. Now, what is this doing? This is basically a G generator. What this does is, if you don't include this statement, the program will still run fine. But if you do this, you are supposed to get the same answers as me, because the randomize function is fixed. This is the manual C that we input in the randomizer function. Now what this is doing is torch.multinomial. What this does is, it will go to the first row of this tensor, and then basically matrix. It will go to the first row of this matrix, take one sample based on any, like the replacement is true. So it will take the highest frequency, highest probability, or the second or the third highest probability number. So if we print ix, we'll get 3, and we'll again get 3 even if we run this program again and again. That is because I fixed the generator. If instead of this, if we remove the generator part, every time we'll get a different answer, and this is exactly what we want. We want a different answer all the time. But I'm just fixing the generator for reproducibility purposes, so that you can, if you enter this very seed into your program, you will get the same output as me, which is 3. So what is 3? We had mapped 3, right? If we print itos of ix, we'll get C. What this is telling is C has a high probability. Like it's not the highest probability occurring bigram or letter, but C has quite a high probability. And let us check that. Let us go to the first row and let us check C. Yeah. So C has occurred 1500 times. So there are 1500 names starting with C. And this is what my point is. We are not choosing the highest occurring letter, which is A. A might be the highest occurring starting initial letter for most of the names, but what we want is randomized choices, and the model is choosing C, which is a very high probability, but it is not at all the highest probability, because we have A, we have K, we have J, M. There are so many letters which have a higher probability, but we also want randomized decision. So the model has chosen C. Now what we'll do is we'll repeat the process that I told you earlier. We'll go in C's row and then choose a bigram with a higher probability. It's not that we want the highest probability, we want a bigram with a high probability. For example, we might choose H, we might get I, we might get E, we might get A, we might get anything. So let's write a for loop. Let's actually make a name generator now. For in range 10, we want 10 names. We want a out variable, or rather we want this. We'll start by ix equals to 0 because we want to start with the first row. Ix equals to 0. Now while true, what we'll do is ix will be the same line, dot multinomial this, and if ix equal to 0, we'll break. Why will we break if ix equal to 0? Because we know that 0 has been mapped to dot. If you see, yeah, 0 has been mapped to dot. And if we get 0 as an output, that means that the name generator has ended its name. That is why we are getting a full stop. Because you know what we have done is dot represents the starting of the names or the ending of the names. So if we get a dot, it represents that the name has been ended. Now there might be a high chance that after starting it might generate a dot again. So there will be a blank name, but that case is rare. But let's just see what happens. And then what we'll do is, if not, then out plus equals to itos of ix, and then we'll print out. Yeah. Okay, something has gone wrong. Okay. Yeah, I get it. Stop. Yeah. We want P. What we want is, we want probs to be equals to P of ix. Yeah. And instead of P of 0, we'll do probs. Yeah. This time we'll get a right answer. Yeah. So now if you see, we have gotten proper names. Like it was much better than what we were doing, choosing the highest frequency all the time. We are getting proper names. ANIR, Anir might be a name, ARAH, Ara, JUS, Dion. So we are getting okayish names. They are not 100% accurate, but they are not 100% wrong. What I mean by this is, let's say what I'll do is I'll do a subtle change here. Instead of making this a probability distribution, what I'll do is I'll comment out everything and I'll for I in range 27, yeah, P of I will be 1 by 27. What this will do is we'll get the same probability for each of the bigrams. Right? P of 0, we'll print P of 0. Yeah. So every bigram has a probability of 3%, 3.7%, right? Instead of actually having different probabilities, proper probabilities to each of the bigrams, we are giving equal probability to all the bigrams. Now you'll see the magic. Now if I generate names, you'll get blabber, absolute rubbish names like EXZM. Like, this is absolute trash. Absolute trash names. Now, this is exactly my point. The names that we were getting earlier, you might be thinking that they are also random letters generated, but no, that is not random letters generated. That is actually getting chosen. Like, the bigrams are getting chosen based on like actual probabilities. So if I run this again, instead of just 0.3037, which is 3.7%, we are assigning proper probabilities to each of the bigrams. And if we run again, we'll get proper names. Yeah, EXZE, lion, whatever. And again, if I remove this G generator, yeah, or rather I'll just remove this. If I remove this, I'll get different names all the time. Yeah. So yeah, I'm getting different names all the time. Zon, Kaino, Tesh. So I'm getting better names. Last time, if we assigned equal probabilities to all of the values, we would have gotten this like very trashy names. But right now we are getting names which make some sense. Mulislia. So these names still makes some sense. But now I'll just replace this so that you also get the same names. Yeah. Okay, I'll run this again once, and I'll get, yeah, Teda, Da, Lion, Exe, whatever. So we are getting some sort of names. This is just the part one. This is not exactly like we are just generating names based on this matrix, right? We have converted this matrix into a probability distribution, and then we are generating names. In the next video, I'll actually make a neural network which will be basically this, but it will actually use neural networks to generate names, and we might get the very same names again. Thank you.